Alright, so for this assignment I did problem 91 from chapter 12, and the problem says that two identical uniform beams are symmetrically set up against each other, as shown in this figure, and on a floor in which they have the coefficient friction 0.6. What is the minimum angle that the beams can make with the floor, that theta value as indicated, and not fall? So it's basically a ladder problem with this sort of a diagram, and I just named the beams L and R for left and right. And then, given this, I created the two torque diagrams. I'll just focus on the left ones. Both are the same. They're symmetric. They're just sort of reflected about each other. And Fr is coming up at the top there. So that's the force the right exerts on the left. There's the force of Earth, and that's the angle it's making with the ground. And I assume that the ground was the pivot for this scenario. And we know that the sum of the forces and the sum of the torque is 0. Same thing for the right beam, where Fl is the force the left exerts on the right, and there's the force of the Earth going down. And the force diagram would look like this if we were to treat it as a point, with the Earth and the normal force from the floor cancelling each other out, and the force the other exerts and the force of friction cancelling each other out as well. Now, one of the key assumptions made here, which the problem does allow us to make, is that they're meeting perfectly in the corner as shown here, so that the normal forces are horizontal as shown in this diagram. So the first thing we set up is that the torque exerted by the Earth is half the length, assuming because it is a uniform beam, times the mg cos theta. And I plug in mg over there, just using Fe over here. So L over 2 mg cos theta. Then the other one is given as L times the force of the other object, sine theta. I used other here just to be general, so that we can treat both beams. And the sum of the torque is just torque of Earth plus torque of the other equals 0. So 0 equals that whole thing. And then solving for F other, we get mg cotangent theta over 2, much like the ladder problem. Then forces in the y direction add up to 0, meaning that the negative mg force exerted by Earth is equal to the normal force as we get over there. Then the force of friction is defined as follows: the coefficient times normal. So when we set up the same identity, it's the same sum of the forces for x, we get that the force other is equal to the force of friction. And so therefore mg cot theta over 2 equals mg mu. And then solving for theta, we get theta equals the cotangent inverse of 2 mu. Now in the problem we're given that mu is 0.6, so taking cotangent inverse of 1.2 gives us 39.806 degrees. And that's the problem I had. It's basically exactly a ladder problem, as long as you assume that these are the normal forces and one been on top of the other. The theta value we have plugged in for the torque exerted by other over here would have probably been different, as the normal force exerted by the other ladder or wall would have been different.